So this is all about the SIR model by Grant Kittichai. So the term S in the SIR model, the term S represents the amount of susceptible individuals in a given population, basically the amount of people that could get the disease and catch it from the infected individuals. Then onto the term I within the SIR model, represents the amount of infected individuals within the population. To detail that more, it's basically the people who are infected with the disease and can pass it on to others in the given population. The term R in the SIR model, the amount of recovered individuals within the given population. So the amount of people that were healthy and disease-free, got the disease, recovered from it, and are now back to being healthy. Also represents the rates of recovery and infection are also just represented with R. So why are I and S non-negative? Well, I and S, they're both the infection and the number of infected and the number of susceptible. So if these were negative numbers, there would be nothing happening basically with this disease. It wouldn't be spreading or existing. So that's why these would be non-negative. But if there was nothing happening, they would just be zero. But they couldn't be negative. That just wouldn't make sense in context of a disease and what it does. So they would just be zero. So basically all of these ds over dt and the di over dt, they're basically all just derivatives of the functions with respect to time t. So this one, ds over dt, is function, if we take s of t, function of time t, then ds over dt is just the derivative of it, and represents the rate of change of the number of susceptible individuals with respect to time t. So why must s be a decreasing function of t? So the equation ds over dt can be set equal to negative asi, with this negative over here while this is positive, while a, s, and I are all positive numbers. So that means that because these are positive with this negative, that ds over dt must be a negative function for all time t, which means that s is a decreasing function for all time t, and that would mean that this is a decreasing function to keep the negative. So getting back to these derivatives of I of t and those, so di over dt is the derivative of I of t, and represents the rate of change of the number of infected individuals with respect to time t. Last one of these derivatives here, so dr over dt is the derivative of r, which is the rate of recovered individuals with respect to time t. Since it's the derivative of r of t, it represents the rate of change of the number of recovered individuals with respect to time t. So to explain why this is set equal to that, if we take s of t and add it to I of t, it makes the term s of t plus I of t. We can so then d over d of t with that is just the derivative. So this represents the rate of change of the number of individuals not yet recovered from the disease. On the other side, b is the recovery coefficient, I is the number of infected individuals at time t. So this means that bi is the rate of change of individuals that have not yet recovered from the disease. So negative bi is the opposite of that, rate of change of individuals that have not yet recovered from the disease. So those both end up with the same value, the same information basically, and should be the same value. Left, kind of like left side equals right side. So at the end of the day, they should be getting the same value, they should be equal, which makes sense, and they are. So, and then just a little extra observation about it. If we make a function for the total number of individuals, s of t, r of t, I of t equals the total, and the derivative of this would look like this, and it would be set equal to 0, while that's set equal to the total. So this would confirm that there are no changes to the total number of individuals. It stays constant. It is like a constant, which makes sense. And in context, this means that all people are recovering from this